In this video, I'm going to go through some properties of piecewise functions and how we use piecewise functions in regards to evaluating their limits, and then how we examine piecewise functions for what is referred to as continuity or points of discontinuity. So we'll kind of get to that as we work through the video. Remember, you can always pause the video, rewind the video if there's something you don't understand. Also, if there's still something you don't understand at the end of the video, you can reach me by email or through our Teams page for any further clarification. So we're going to start by going back to looking at a piecewise function, which we did look at these in Pre-Calc 12a in our functions unit. This would be an example of a piecewise function. Now, piecewise functions are functions that do different things depending on what kind of an x value you choose to substitute. So for example, in this one, if I pick an x value that's smaller than or equal to the number 2, then this function, I'd use this piece. However, if I'm looking at an x value that's more than the number 2, then I would use this piece of the function. So just this dictates out here which piece of the function you use. So for example, if I wanted to figure out f at 1, that's asking me to figure out what is the y value when x is equal to that number. Well, if I go up here and say, well, if x was 1, it would be a number that's smaller than or equal to 2. So I should use this piece of the function. So f at 1 would be 1 plus 3. F at 1 would be 4. If I wanted to do f at 3, well, this is my x value. This time x is more than 2, so I should use this piece of the function. 3 squared minus 2. F at 3 would be 7. Now, the one that sometimes will confuse students, they'll say, what about if it's actually the number 2? Well, if x is equal to the number 2, you'd use this piece of the function because it says this is for when x is less than or equal to the number 2. So therefore, I'd put 2 in here for x, 2 plus 3, and I would get 5. So that's a relatively easy concept. It's just a matter of looking at the domain out here and determining where you're going to substitute into the function, which piece of the function you're going to use. Now, the next part is taking this piecewise function and drawing a sketch of it. And we did do that also in Pre-Calc 12a. So we'll just quickly refresh your memory on how to do this. First thing you got to do is basically draw 2 graphs on the same axis. So I'm going to f of x is the same thing as y equals. So I'm going to graph y equals x plus 3. And I'm also going to graph y equals x squared minus 2. And then I'm just going to put them both on the same grid. Well, it's not completely random what numbers you pick here for x. You always have to make sure you include what I'm going to refer to as the boundary number. The boundary number, what I mean by that is this number 2. 2 is kind of the pivotal number where the function stops doing this, and then on the other side of 2, when x is more than 2, it starts to behave this way. So I need to know where's the graph at that point where it switches behavior. So I need to know where it is when x is 2. Now, this is a line, so I need at least one more point. So I'm going to pick some other number as long as it's less than 2. So I'm going to use, let's say, 0. You could use any number you want for this one, less than 2, but this one has to be the boundary number. Put that 2 in here for x, so I'm going to get 2 comma 5, 0 plus 3. That's all I'm going to need for this one. Now over here, now we do assume that you know some general properties of functions. So I knew this was linear because it was x to the first. I should know that this is a parabola because it has the x squared. So this would be a parabola. It would open up because it's got a positive out here. Its vertex would be at 0 because there's nothing added or subtracted to the x squared. So it would be 0 comma minus 2. Now, unfortunately, that's a point I'm not going to be able to see. You say, well, why can't you see that number? Because if you look at it, the x value is 0. Well, it only acts like this parabola for x values that are more than 2. So 0, negative 2 is not going to be a point we're going to be able to see on this graph because the x value is actually less than 2. So if the x value is less than 2, it's going to be behaving like the line, not like the parabola. Like this one, the first number you need to put in here is your boundary number. Fill it in here. 2 squared is 4. 4 minus 2 is 2. I know it's a parabola opening up. I'm going to get one more point, so I'm going to pick, but you got to make sure you pick a number in the interval. So I'm going to pick, let's say, 3. 3 squared is 9. 9 minus 2 would be 7. So now I'm ready to just draw a quick sketch, nothing too fancy. I don't need to get graph paper out or anything like that. I'm going to take, and let's look things over here. So my y values go up to 7. My x's, everything's positive. So if I just have a graph that looks something like this. 1, 2, 3, 4, 5, 6, 7. I'm going up by ones. My x's go over first 3, so let's say 1, 3, 4. It should do it. There's 4, 2. I'm up by ones. These are my x's. These are my y's. Switch colors. So now I'm going to plot these points. Now there's one thing you got to watch for, the boundary numbers. So the boundary numbers, I'll just highlight them again, where the ones that have, you'll notice that 2, and that'll sometimes confuse students and say, how can you use 2 in this chart and you use the same number again over in this chart? How can it be in both? It's not going to be in both. And the way we'll distinguish that is with either shading in the dot when we plot it or leaving it open. And the way you distinguish that is if you look up here at the inequality symbols, less than or equal to, you're going to shade that point in when you plot it. This one, when you plot it, because it has no equal sign with it, that's going to be represented with an open circle on my graph or an open dot. So if I go down here, and let's start with the line 2, 5. So 2, 5. 1, 2, 3, 4, 5. Remember I said I'm going to shade this one in, fill it in, because it's got an equal sign. 0, 3. And then we're going to make a straight line best we can. Right out through those. Goes forever that way. Nothing to stop that in that direction. Then I've got 2, 2. So 2, 2. Now watch the difference. This one had no equal sign. So when I draw it, I'm going to make an open circle. 3, 7 would be up here. Now, we're going to let you get away with just using 2 dots, provided that you're going to show us you have a little bit of knowledge of what's going on. You're not going to take these 2 and make a straight line through them. You got to realize that the vertex, this was a parabola, which would be coming up through here, but we can only see this part of the parabola. So we're going to make sure this is slightly curving up, and again, it keeps going forever. So, well, how do you know it keeps going forever? Because it said that this interval was for any x value more than 2, and this interval was for any x value less than 2. And there would be your sketch of that piecewise function. So that's kind of a recap of 12a. Okay, so let's suppose I wanted to draw the sketch of this graph right here. Well, to do that, I've got 3 functions. Basically, I've got to sketch. I've got to sketch y equals 1/2 x minus 2. I've got to sketch y equals -1. And I've got to sketch y equals x minus 2 squared plus 1. 3 functions, but they're all going to be put together on the same grid. We're going to make 3 tables, x and y. This is linear because it's x and y to the first power. I have to choose the boundary number. That's the first number I always put in my chart. So that's -2. Fill it in here for x. So 1/2 of -2 is -1. Take away 2, -3. Now notice there's no equal sign this time on the top interval. So when I plot that ordered pair, I'm going to use an open circle. Now I'm going to pick any x value I want that's less than -2. Well, remember, whatever you're allowed to pick whatever you want here. So pick something you can take half of, something that's easy. So you don't want to pick 1, or sorry, you don't want to pick -3 or something like that. I'm going to pick -4. 1/2 of -4 is -2. Take away 2, that's -4. Those 2 points would be enough to get what that looks like. Y equals -1, you shouldn't need anything. That's just a horizontal line. And it's passing through y equals -1. Now it's got to start it, so it's going to start at -2, filled in, and it's going to go straight across until you get to +1, also filled in, because there's equal signs at both of those. So we'll take care of that when we sketch it. This one's a parabola. I'm going to write out the vertex here just so the vertex would be at 2, comma 1. This time, there's one point I can already use because that's that x value. There's your x. It's more than 1. So there's a second point that I already have. You say, what do you mean by second point? Well, your first point, remember, always has to be your boundary number right there. So I'm going to use 1. Fill it in here. 1 minus 2 is negative 1. Square negative 1, you're going to get positive 1. Add 1, you're going to get 2. That's all I'm going to need. That boundary point, which will be, notice, no equal sign. That'll be an open circle. And then I'll use this second point, my vertex. And then I'm going to use what's called symmetry. You'll see what I mean by that in a second. And I'm going to use that to make my sketch. All right, so we're going to go down. Look your numbers over so your graph will fit them all. So I need my y values to go down to -4, up to 2. My x's go over to -4, and then over to 1. So I just want to make sure my graph will hold all the points that I need. Oh, too far. Okay, here we go. There. So my y values, I'm going to make them go up to 2. 1. Make sure these are roughly the same width. Don't have to be perfect. 3. There's -4. Now my x's, I'm going to go over, say, to 1, -1, -2, -3, -4. Okay. Now we're ready to start plotting points. All right, so -2, -3, you always have to go back and look here and say, am I going to fill it in or am I going to leave it as an open circle? In this case, because there's no equal sign, that order pair is going to be an open circle. -2, -3, -2, -3, open circle. Then I'm going to use -4, -4. Now, the only time you're worried about open or closed circles is at the boundary. Every other number is always going to be a full shaded in circle. So -4, -4 would be roughly down here somewhere. It's linear. Make a line that goes out through those, and it will go that way forever. And you can say, well, how do you know it goes forever? Because it said for any x value less than -2. Next piece of the graph, y equals -1. And this is going to do this, behave this way for any x value that's, once you start at -2, filled in, and when you finish at +1, filled in. So -1 is the y value all the time on this horizontal line. So at y equals -2, filled in, 1, filled in. There's the graph of y equals -1. Those dots are filled in because of the two equal signs. Last piece of the graph. We had our boundary at 1, 2. There was no equal sign, so that's going to have an open circle there. We had our vertex at 2, 1. So 2, 1, that's the vertex. Now again, think this is the vertex, so this must be the left side of the parabola. The parabola is going to come down here. Now what students will sometimes do is they'll just make a line down through here. It's not linear, it's a parabola. This is the vertex. Using what's called symmetry, that means if I go over 1 and up 1, there should be another point over 1, up 1 right here. And then your graph should take on the shape of a parabola. As far as these arrows go, there's only going to be arrows on the last interval and your first interval on your piecewise function. The one in the middle, you can't put arrows on this because then that would mean that the function is going to continue over here and it's going to have to behave like two different things in one spot. That can't happen. Same thing here. If you made that arrow go this way, well then all of a sudden the function is going to be doing two different things in one x value, which we can't have happen. So that would be an example of this sketch. All right, moving on to limits. So we want to be able to, if you think of the first two slides. I'm really just trying to refresh your memory on some skills that you should have brought with you to the course. Now we're going to get into how does this tie in with what we're doing this year in terms of limits. Well, if I looked at this one, for example, what's the limit of this function up here as x approaches -1? Well, if you think back to limits, when it didn't stipulate left side or right side, it implied that we were checking both of those. So this was, even though it doesn't say it, I need to figure out what is the limit of this function as x gets close to -1 from the left side, and what is the limit of this function as x gets close to -1 on the right side. And if you recall from our study of limits so far, in order for us to get an answer here, like equals 6, equals 10, equals 5, equals some number, the left side and the right side have to both be getting close to the same number. In these ones, just taking -1 and filling it in here is not going to be sufficient because of the fact that at -1, this graph is switching behaviors. Now, if it was at x is 0, sure, just fill 0 in here. It's these boundary numbers, but that when you check their limits, you've got to be very, very careful that the left side and the right side are giving you the same number. Otherwise, it's going to be it does not exist. All right, let's have a look at this one. So -1 from the left side. Left side, if you have a number line, there's -1. That would be 0. That would be -2. If you go to the left side of -1, well, that's another way of saying less than that particular number. If you go to the right side of -1, now you're talking about numbers that are greater than -1. So that's going to be how you determine which piece of the function you use to check your left and right side. So for example, if I want to check the limit of this function as x approaches -1 from the left side, that's implying that the x values are slightly to the left of -1. Well, if they're left of -1, they're less than -1. Here's -1. Any x value that's less than -1, x is less than -1, you're in here. So I'm going to put -1 in for x in the top piece of the function here. So this will equal, again, wherever there's an x, I'm going to replace it with -1 minus 2. And that's going to give me, you got to be careful here now, it's negative, negative, so that's really +1, minus 2, that's going to give me -1. Then I'm going to check the right side of -1. So now I'm dealing with x values that are slightly more than -1. Well, if the x values are slightly more than -1, it says right here, if x is greater than -1, you're going to use this piece of the function. So you're going to put -1 in for x, which gives me -1. So I now check my two numbers and say, well, they're the same. So if they are the same, that is the answer. So the limit of this function as I approach -1 is -1. Okay, let's move on to 1. If I check this piecewise function at 1, which is another one of your boundary numbers, I've got to check left and right side to see what happens. So I'm going to go limit of the function as x approaches the number 1 from the left side, and then what is the limit of this function as x gets close to the number 1 from the right side. So remember, 1 from the left side implies that the x values are slightly less than the number 1. And we mean like ever so slightly less than the number 1. So if you're picking a number that's ever so slightly less than 1, you're going to be dealing with this piece of the graph right here. So you're going to fill 1 in for x. And again, then you say, well, how do you know if you're putting 1 in for x? That's the function in that interval. F of x in this interval is equal to x. So I just fill that number into the function where there's an x. This one, as x is approaching 1 from the right-hand side. Now I'm talking about numbers that are ever so slightly greater than 1. Well, if a number is ever so slightly greater than 1, you're in this piece of the function. So I'm going to put 1 in here where the x is. 1 squared minus 2 times 1. 1 subtract 2, I get -1. Now, unlike the last time, over here, these were the same. So our answer was that number. The left side is 1. The right side is -1. If the left side and right side are different, then our answer up here is going to be does not exist. Reason being, limit as you approach the number 1 from the left and the limit as you approach the number 1 from the right are different. All right, so there's your first example of how you can evaluate limits as you're dealing with a piecewise function. Oops. All right, let's have another look at one more of those just before we move on to what's called continuity. And again, you're going to find that they're always going to ask you, generally, the limits as you're approaching these numbers where the function switching behaviors. Well, let's check 1. So I need the limit of this function as x approaches 1. I'll go from the left side first. That means slightly less than the number 1. So if x was slightly less than the number 1, I'm going to fill x as a 1 in here. So 2 minus 1 squared, I'll get 1. Check the limit of this function as we approach 1 from the right side. This implies that the x value we're going to pick is slightly greater than the number 1 because it's on the right-hand side of it on a number line. So if x is slightly greater than 1, now sometimes students say, well, I don't know how to use this one. Remember, we're talking about just ever so slightly more than 1, not 4 units away from the number 1 or 2 units away from the 1 or 1 unit away from the 1. We're talking like just on a number line, there's 1. That number right there, that's x is approaching 1 from the right side. So that tells me to use this piece of the function. This is when x is ever so slightly more than 1. Put 1 in here. 2 times 1, which will give me 1. These two are the same. That means the answer is a 1. Let's try 3. Now sometimes you can say, yeah, but what about this one? We're not concerned with that one because that's when x is actually equal to the number 1. Remember, limits are when you're getting close to the number, but not equal to the number. Now we're going to check 3. Same process. We're going to find the limit of this function. Notice my notation too. Please make sure you get in the habit of writing it out properly. Limit of the function as x is approaching 3, whatever. Let's say I go right side first. So that means the right-hand side of 3, we're ever so slightly more than 3. If x is greater than 3, which would put me here, I'm going to use this. 3 take away 4 squared. -1 squared is +1. So now, in order for the limit to exist, I've got to get 1 here. If I don't get 1, it does not exist. So now I'm going to check 3 from the left. That implies that x is ever so slightly less than 3. If x was ever so slightly less than 3, we're in this piece of the function. 2 times 3 minus 1, 6 minus 1, 5. Notice they're different. That would imply this limit does not exist. All right, so that's how you read limits or evaluate limits when you're dealing with piecewise functions. So the whole idea of checking from the left side and the right side becomes very, very important. All right, so we're now going to take what I've discussed in the introduction leading up to this, where we looked at piecewise functions, what they are, refresh your memory on that, and then we get into how to read limits from them. We're going to put that stuff all together, and we're going to examine something that is referred to as continuity. Now, it's one of those things that if you look at it in a calculus textbook, you think, oh my goodness, this is so complicated. But really, when you break it down to examine continuity, it's really not very difficult to do at all. So don't get kind of wrapped up in the, the words you'll see here, because I've taken some slides right out of calculus books and say, oh my goodness, this sounds so confusing. It's really quite easy to check. All right, so here's just telling us what continuity is. We noticed in the preceding section that the limit of a function as x approaches a can often simply can be found simply by just filling in the value at a. If you can do this, then this function is said to be continuous. Oh, well, that sounds easy enough. That implies three things need to be true in order for that to happen. In order for that to happen, this is the definition of continuity. When you find the limit of the function as you approach a, you have to get the exact same answer as when you substitute a. So this is over here is when x is equal to a. This part of the left side of this would imply you're picking numbers just to the left and just to the right of a. When you do that and get an answer, and then when you actually fill in the number, you're getting the same answer. That will be the condition we use to check for continuity. So that's going to imply three things. Number one, the function's got to exist where you're checking for continuity. The limit has to exist, which implies left side and right side. And then the limit has to be equal. So the answer you get here and the answer you get here, they need to be the same. If you don't get an answer here, it's discontinuous. You don't even got to check this other stuff. So if you get an answer here, you don't get an answer here, it's discontinuous because your limit doesn't exist. And then the only way that this one will fail is, let's say you get an answer here, you get an answer here, but the two answers are different. Then it would fail continuity for that reason. These are the three mathematical reasons. You're going to notice when I give you these questions, it's going to say, yeah, check the following function for continuity. If it's discontinuous, provide a mathematical reason. So these would be one of the three reasons you're going to pick. All right, so let's look here at this picture. Here's a picture of a graph that is continuous. Now, as your brain would probably be leading you to think, continuous just means basically that everything all meshes together and fits together perfectly. I'll show you an example in a moment of what discontinuity looks like. But this is a picture of a graph that is continuous every single place that I pick. So if I pick here, when you come from the left side, you come from the right side, you're getting close to that number. When you fill that number in, you get that pink dot as well. So left side, right side, and at the number are all the same thing. They're all getting close to that number, whatever it is on the y scale. That's a picture of what we mean by perfectly continuous, or what they call continuity. Here's some pictures of what happens when it's discontinuous, and I'll give you the mathematical reason for each one of them. Okay, so if I look, let's just go left to right like we're reading a book here. Well, the first issue I would have with this one right here, I kind of look up above, is it's discontinuous because if I tried to find the value of this function at the number 1, there is none. It does not exist. If I said, what if x is equal to 1? Well, there's nothing there, and there's nothing up there. F at 1 doesn't exist. Therefore, discontinuous at that number. At x is 1. Okay, so that's why that one would be discontinuous. Now, the limit, if you say, what about the limit part? Well, the limit from the left, the limit from the right, they do exist. The hole in the graph doesn't matter. That's just at the number 1. Left side and right side are both getting close to whatever that number is on the y scale. So the limit would exist. The problem is the function doesn't exist at that number. Okay, let's look at 3. Well, f of 3. So I said if x is equal to 3, look at that, I got a dot this time. So it does exist. So f of 3 exists. There's condition, I'll just number them. Condition 1, f of 3, check. We got a number. I don't care what it is as long as I get a number. Number 2, what about the limit of the function as you get close to 3 from the left side and the right side? Now this is why we learned earlier on how to read limits from graphs. If I was getting close to 3 from the left side, I'd be hitting the graph down here somewhere, close to that number on the y scale. If I jump to just ever so slightly to the right of 3, now I hit the graph up here. So you can see that from the right side, you're hitting the y scale up there. From the left side, you're hitting the graph on the y scale down here. Well, the problem is they're different. The limit of this function as x approaches 3 from the left, I don't want a 1 there, as x approaches 3 from the left is not equal to the limit of this function as x approaches 3 from the right side. Therefore, discontinuous at that spot. x equals 3. So then we come here to number 5, or at x is 5. Again, anywhere the graph's all nice and smooth and connected like this, there's never an issue with continuity. So it's all fine. So that was an issue. That's an issue. Now we got to examine and say what's going on here. Well, let's start with 5. Do I get a value of the function if x was equal to 5? Well, if x was equal to 5, I'd hit that dot right there. That one, we passed condition 1. We got a number. Again, I don't care what it is, as long as you get a number. Well, what about if I checked from the left and the right side? So if I go to 5 and come from the left, I'm getting close to this number on the y scale. If I come from the right, I'm getting close to the same number. So the limit of this function, as x is getting close to 5 from the left, is the same thing as the limit of this function when you come towards 5 from the right side. However, here's the problem. The answer we get here and the answer we're going to get here are not the same thing. So it is going to be discontinuous for this reason. The value of the function at 5 is not equal to the limit of the function as we're getting close to 5. They'll sometimes refer to this situation right here. You'll see them in some textbooks, or some professors or instructors will call it what's called jump discontinuity. Now, the reason they call it jump discontinuity is because as you're coming from the left and the right, you're getting close to this, you're zeroing in on this number on the y scale, and then all of a sudden when you actually pick that number, it jumps somewhere else to a dot, and they'll refer to that as jump discontinuity. Okay, so there's basically, that's the only way, 3 situations where graphs can be discontinuous. Function doesn't exist, but the limit does. Function exists, but the limit doesn't because left and right are different. Limit existed, function existed, but they were different. So those are the 3 conditions for continuity. All right, let's look at how we're going to check that. So let's suppose I had this graph and I wanted to do a continuity check on it. Well, the first thing you got to determine is, well, where am I concerned about continuity? You're concerned about continuity anywhere a graph switches behaviors. So for example, see how this is at -1 and it's doing this. And then when you go to the right of -1, it starts to do this. That's a number I'd be concerned with. Is there going to be a gap or a hole in the graph or something strange going on there? So when I do my continuity check here, I'm going to, I'll do the one for x equals -1 right here. So if I was checking x equals -1, you basically check the same 3 things every time. What's the value of the function at -1? That's step 1. Step 2, what's the limit of the function as you approach -1 from the left? And then what is the limit of the function as you approach -1 from the right? These are usually easy enough, you can just tell by looking. In order for a graph to be continuous, I'm just going to put a little highlighter down here. The answer you get here, the answer you get here, and the answer you get here have to be the exact same number. If they turn out to be different, this function is going to be discontinuous at that particular number that we're checking right now, which is -1. All right, so let's do our calculations. F at -1. So this is saying if x is equal to -1, not close to it, equal to it. Check your intervals over. Well, this one. If x is greater than or equal to -1, this is your y value. That's going to be a 4. All right, -1 from the left. That means ever so slightly less than -1. If x is ever so slightly less than -1, you're going to be in here. So it's going to be 3 minus a -1. That's going to give me 4. If x is ever so slightly more than -1, so if x is greater than -1, you're going to use this piece of the function again, which I've already used once up here. That's fine. Sometimes you'll use it here and here. Well, the value of the function when I fill in -1 is 4. When I come towards the function from the left, I'm getting close to 4. When I approach -1 from the right-hand side, I'm getting close to 4. That tells me that this function, so this is kind of your final piece of the puzzle, the function when I filled in -1 gave me the same answer as when I checked the function and its limit when x was getting close to -1. Therefore, my conclusion, it is continuous at that spot. Which means if I looked at the graph, it would be all fitting together perfectly. There'd be no hole in the graph or a gap in the graph. Sorry, I kind of overlooked this here. So basically, this is just to simplify things. If there's a gap or a hole in the graph, you have what's called discontinuity. This over here is how you check mathematically which point of, or which condition of discontinuity, what's the mathematical reason why it's discontinuous. So here, I have continuity, so I don't got to worry about providing my reason. Now I'm going to check 2. So let's scroll down a bit so I get some more room. And I'll check continuity as x is approaching 2. You say, why'd you pick 2? Because that's the other spot on the graph where this graph switches doing this to this, and then there's something going on here. All right, let's check the value of this function when I fill in 2. So we're checking continuity now at x is 2. So if x is equal to 2, the y value is 1. Check the limit, and all you got to do is get any number here. If you get any number here, you've passed condition 1 of continuity. Condition 2 of continuity, you got to check the limit of the function from the left and the right, and they need to be the same, or you're going to fail continuity. X is approaching 2 from the left, and then the limit of this function as x is approaching 2 from the right. 2 from the left will be a number that's ever so slightly less than 2. So if x was ever so slightly less than 2, there's your y value. If x was ever so slightly more than 2, now again, so what about this one? That's only when x is equal to 2. I'm doing limits now, so I'm close to 2 but not equal to 2. This would be slightly more than 2. So if x was slightly more than 2, I'm going to get 8 minus 2 squared, which is also 4. Now, let's look at what happened here. My limit from the left and right is the same. They're 4. So that tells me that as I look at the graph, left side, right side, they're getting close to the same number. The problem was when I filled in the number 2, the actual y value isn't 4, it's 1. So on a graph, just quickly, if I pick 2, here's 2, and I've got, let's say 4's up here, 1's down here. So this is telling me that when I approach 2 from the left and the right, 2 from the left, 2 from the right, I'm getting close to that number. So whether it's, I don't know what's happening, but something like that. But then when I fill in the number 2, according to this, the graph has a y value of 1. Well, this is that example we talked earlier about. That's jump discontinuity. Limit existed, function existed, but they're not the same thing. So therefore, we have a point of discontinuity. And here's the mathematical reason. The function, when I substitute 2, f at 2, is not equal to the limit of the function when the x value is getting close to 2. That's called a mathematical reason. That is the mathematical reason for what I refer to as jump discontinuity. So my conclusion is, therefore, f of x is discontinuous at x is equal to 2, which implies there's a hole in the graph, which I just showed you right here. This type of situation is what's going on at 2. Now it asks for the sketch, but I'm not going to get into the sketch just because it's a little bit time consuming and I don't want the video to run too long here. So the number one priority I have right now is just for you to be able to check continuity without having to actually rely on a graph. Okay, let's look at another one. All right, here's one which again, we're just going to do part A. I'm not going to get into the sketch at this one. If I wanted to check this for continuity, so the first thing you got to figure out is where you're concerned about. What issue do you have? Well, I'm concerned at 1 because of the behavior change of the function at 1, and I'd also be concerned here what's going on when x is 3. So let's check each of those individually and see what happens with our continuity check. All right, so let's start with this function. What happens when I fill the number 1 in? Do I get an answer? Not there, not there, but I do right here. If f is 1, I'm getting 3. Condition 1, met. What about the limit of this function as I approach 3 from the left and then from the right? Again, in order for it to be continuous, I have to get the same answer here. So let's just scroll down a bit. 3 from the left. Sorry, not 3 from the left. Why do I have 3? That should be 1, not 3. That didn't confuse you. I was looking here instead of up here. We're looking at 1 for our continuity check. It should be 1 from the left and 1 from the right. So 1 from the left and 1 from the right. Okay, so if I check each of those, 1 from the left implies slightly less than the number 1. That's here. So let's fill 1 in here. Now, eventually you'll just write an answer down here. I don't want to confuse you with where I'm getting these from. So I'm filling 1 into that top piece of the function, which will give me a 1. 1 from the right implies that x is ever so slightly more than 1. If x is more than 1, we're going to fill it in here. 2 times 1 minus 1, which will give me 1. Left side and right side, same. So this limit exists. This function exists. Now it's much like the last one we just checked. Even though the limit exists and the function exists, the problem is they're not the same answer. Therefore, that's jump discontinuity. The limit of this function as the x value is getting close to the number 1 is not the same answer as when I fill 1 into the function. Therefore, discontinuous at 1. Now, what we're checking for here are points of discontinuity. Sometimes students say, oh, I already checked at 1, it was discontinuous. I'm not going to bother over here. We're not throwing in the whole function out. We're just checking on the function where are points of discontinuity. All right, let's try 3. Get our function again. So the first thing I got to check, what if x is equal to 3? So when I put the number 3 into the function, not a limit, go up here and say, okay, where is x equal to 3? This interval. 2 times 3 minus 1. F at 3 is 5. Now check, does the limit exist? Well, to figure that out, I got to check the left side. So x is approaching 3 from the left. Slightly less than 3. It's going to be the same piece that I just used for when x was equal to 3. So 2 times 3 minus 1. We're also going to get 5 for this one. Let's check the right side. The limit of this function when x is approaching 3 from the right side would equal this piece of the function. So x is more than 3. This is what the function is going to behave like, this quadratic. So I'm going to fill 3 in for the x and see what I get. 3 take away 4 would be negative 1. Squared would be 1. All right, we have an issue here. The left side and the right side are not the same. That implies visually, if you picked 3 on a graph here, the left side's going one place, the right side is going somewhere else. There's a gap in the graph. So as soon as these are different, it's discontinuity because there's a gap in the graph. Therefore, I'm going to say, therefore, oh, actually, let's say, therefore, the limit of this function as x is approaching 3 does not exist, which then leads me to the conclusion f of x is discontinuous, means it has a hole or a gap in the graph, discontinuous at x equals 3. So over here, it was discontinuous because the function value and the limit of the function as you get close to the same number, and as you equal that number, were different. Over here, the reason for the discontinuity was not that. It's because the function existed, the limit existed on the left and the right. The problem was they were different, which leads me to this conclusion. The limit of this function as x gets close to 3 does not exist. Therefore, this function is discontinuous at 3. Now, I'm not going to go through, that's two good thorough examples, so you can rewind, watch them again. I do want to show you what does it look like if you fail that very first condition, because sometimes students say, well, how does that not happen? I'll see if I can find one here. I think this one has it. Here's one right here. If we just jump and look at this function down here, and I said, okay, I'm worried about what's going on at 5. Let's check this function at 5. So this means not x is close to 5. This means if x is equal to 5. Well, go here and say, this interval is for if x is smaller than 5. Okay, well, this interval is for if x is more than 5. Wait a second, what if x is equal to 5? It doesn't fit here. It doesn't fit here. There's nowhere where the number x equals 5 fits into any of these intervals. Therefore, f at 5 does not exist. And the beauty of that is, you don't got to worry about anything else. Therefore, discontinuous at that number. You don't even got to check the limit at that point. Ugh, my writing's getting bad. Discontinuous at x equals 5, because that implies there's a hole in the graph. When x is 5, whatever's happening left side and right side, at the 5, there's an open circle, and there's no shaded in dot anywhere where when you fill in 5, you get some y value. So that's how you fail that first condition of continuity. Okay, so that's an overview of piecewise functions, how to evaluate piecewise functions and draw them. That's a recap from 12a. I looked then at how to evaluate the limits of piecewise functions, and then we took all of that information, put it together, and did what's called a continuity check on a function, and we learned how to examine piecewise functions for any points of discontinuity. So hopefully this video will help you with those concepts. I'll give you a chance to watch through the video first, and I will then give you some examples of things you can use to practice, and that will then be followed up with a little assignment on piecewise functions and their limits and continuity. Good luck with that.